Okay, now I will do some examples. Continue this lecture. Okay, um, I think this is this video, video number 4, right? Uh, Continue this video. Right, first this example, right? Example 3.2.18. A parcel order in any set, right? The parcel order, the parcel order in any set, in any set A of A of real, right? A of real numbers, right? With a natural order. You already know the definition for the natural order, mean less than equal natural order, right? With a natural order, right? Natural order is a total order, right? Is a natural order, right? Natural order is a total order, is a total order since any two numbers are comparable. Since any two numbers are comparable. Okay, solution for this part. You know that here there are n elements a1, a2 and an less than equal is natural order b1, b2, bn. Okay, if and only if each of ai less than equal each of bi coordinate wise in the natural order in real number. In the natural order in real number. Okay, the natural order in real number. Therefore, you want to show that reflexive, antisymmetric, transitive, then you consider it is a partial order, and each of the elements like this. Ai less than bi means each of the elements is comparable. Therefore, it is a totally ordered set. It is a solution for this part. Okay, it is the totally ordered set. Now, since a1, a2 and an less than equal a1, a2, an, that is if and only if no ai less than equal ai for all, right? For all ai belong to real, therefore reflexive. Okay, therefore reflexive. For a antisymmetric case, right? For an antisymmetric case, right? For an antisymmetric case, if a1, a2 and so on an less than equal b1, b2 and so on bn. Okay, and you want to take again b1, b2 and so on bn less than equal a1, a2 and so on an. From this two you can write if and only if no, therefore ai less than equal bi, and from this part bi less than equal ai for all ai comma bi belong to real number. Okay, for all ai comma bi belong to real number, right? Therefore from this two each of ai equal to bi for all I belong to one of the index set ai comma bi belong to real number. Okay, therefore antisymmetric. This relation is an antisymmetric relation. Next, for a transitive, same idea again. Let a1, a2 and so on an less than equal b1, b2 and so on bn. Okay, b1, B2 and so on Bn. Okay, again, and B1, B2 and so on Bn less than equal C1, C2 and so on Cn. From this two, from first part you can write Ai less than equal Bi, and the second one you can write Bi less than equal Ci. From this both you can write Ai less than equal Ci. That means A1 up to An less than equal C1 up to Cn. Therefore transitive called, right? Therefore transitive. That relation is transitive. Right, transitive. Therefore reflexive okay, antisymmetric okay, transitive okay. Therefore this partial order in any set A of real numbers with natural order is a totally ordered set, because, right, from this one transitive, then you can write it is, right, here last one is a transitive. Therefore reflexive okay, antisymmetric okay, transitive okay. Therefore it is a partially ordered set. Therefore it is the relation is a poset, right? The relation is a poset. Context I can write here. Each of the elements are comparable, therefore it is a totally ordered set. Therefore the relation is a poset for all Ai less than equal Bi. Each of the elements are comparable for all Ai, Bi belong to real. Each of the elements are comparable. Therefore, it is a chain. That means it is a total order set. The other name, chain. Okay, therefore it is a chain or total order set. Right. Next example. (3.2.19). Let R be a partial order in V partial order in V. The P set equal 1, 2, 3 and so on up to 6. 3, 4, 5, 6. Defined by X divides Y. Defined by X divides Y. Then R is not a total order. Why? Because elements not comparable, no? Order in V. Totally order, partially ordered set okay for X divides by, but not a totally ordered set, right? One, two, up to 6. I think we already did, no? This like this problem. 1 to 6, yeah. 1 to 6 already did. I think example 2 point, right? 3.2.6 we proved. We already proved. Okay, we proved this B comma this partial order relation is a poset. Already proved this part, right? It's a poset, and now you take two elements, right? You take two elements, then both not comparable. Therefore, you can say that it is not a totally ordered set. Here you can take two arbitrary two elements. 3, 5 belong to this set V. Okay, but 3 does not divide 5. Therefore, 3 and 5 are not comparable. For each element is comparable, okay. Here at least for one arbitrary you take one element, but that one element also is not comparable. Therefore, it's not a totally ordered set, right? Not comparable. Therefore, R is not a totally ordered set. R is not a totally ordered set. Okay, R is not a totally ordered set. Okay. Okay. Um, Therefore, R is not a totally ordered set. This example, right? 3 divides 5. 3 divides 5. Yeah. 3 does not divide 5. Right? Right? Okay. Next example, right? Next example I will do. Example 3.2.20. Let A be A comma B be totally ordered sets. You know the Cartesian product. This Cartesian product also totally ordered set. It is another name for a Cartesian product. It is a totally ordered set. They mention another name to that one, right? That one also totally ordered set. Okay, that theorem I want to prove, right? A cross B also totally ordered set, right? That part example, this example I can do. I can write other side of both. Okay, okay, right. This example 3.2.20. Let A and B be totally ordered sets. Let A and B be totally ordered sets. then the Cartesian product, then the Cartesian product A cross B can be totally ordered as follows. As follows. Okay. You take A comma B, so order, proceed A dash, B dash, if this condition satisfying, right? A less than A dash, okay? A less than A dash, A less than A dash, or A equal to A dash and B less than equal B dash, okay? B less than equal B dash. This order is called as one of the specific name. This order is called the um, lexicographical order of A cross B since, right, since it is similar to the way, right, it is similar to the way it is similar to the way words are arranged, right, in the dictionary, right? That means you can write another name for this partially order set as a dictionary order, right? Arranged in a dictionary. Okay. Okay. Arranged in a dictionary, right? Right. It's clear. Okay. Right. This uh, lexicographical order of A cross B, since it is similar to the way words are arranged in a dictionary. Okay. Right. Now you want to prove this one is a partially ordered set. So totally ordered set. Right. For a reflexive, for a reflexive, here they asked to only prove here ordered sets, then Cartesian product A cross B can be totally ordered as follows. Therefore, first of all, we want to say that partially ordered, but here all elements are comparable. No, here A less than A dash, A equal A dash means A less than equal A dash, B less than equal E dash. Therefore, each of the element of this set comparable. Therefore, this is a totally ordered set. That's all. First, A comma B, proceed A comma B. That one, from this two things, suppose A comma B, again A comma B means A less than A dash, not possible. A less than A not possible. Therefore, A equal A dash. Therefore, A equal to A, no, it is possible. That means since, therefore, since from this two, A less than A dash, A equal A dash, therefore A less than equal A dash, therefore A less than equal A, and obviously B less than equal B dash means B less than equal B. Right? From this both, therefore reflexive. So here reflexive, here below, therefore reflexive. Antisymmetric case, let A comma B, right, A dash B dash, and A dash B dash A comma B. This means A less than A dash or A equal A dash and B less than equal B dash, and A dash less than A or A equal A dash and B dash less than equal B for this case. Okay. Here, this A less than A dash, right? It is not possible because A less than A dash, right? A less than A dash, but here equal. Here A dash less than A equal A dash. Here, in this case, okay, in this case, the first case means this one, A less than A dash. A less than A dash is impossible, right? Why? Why is impossible? Impossible means here you have the case A less than A dash, but you already have the case oh this one or this one. But again you have A dash less than A equal A dash. From this both here, suppose A less than equal A dash and A dash less than equal A, therefore both are equal, no? Therefore this is not possible. Equal only possible, right? Since this would contradict, right? Contradict to this part, A equal A dash. Okay, contradict, right? Contradict. Therefore, this one possible means A equal A dash equal A. Therefore, A equal A dash one case. Again, B less than equal B dash is obviously true. B less than equal B dash and B dash less than equal B means B equal to B dash. That one means, right? That one means from this relation, this A comma B related to A dash B dash there, no? In this relation, it is not possible means A should be equal to A dash. Since you have, right, since you have A comma B, A comma B, this relation, A comma B, A dash B dash. In this one, for a Y case, you have from this part B less than equal B dash. But here, A dash B dash is related to A comma B. This case, proceed A comma B means this B dash less than equal B. This both you can have B equal to B dash. Here A equal to A dash, B equal to B dash. Therefore, no, A equal A dash, B equal B dash means here A comma B equal A dash B dash. The coordinate wise equal, right? The coordinate wise they are equal. Okay, therefore coordinates phi both are equal, therefore it is antisymmetric. Therefore antisymmetric. The relation is antisymmetric. Therefore antisymmetric. Okay, reflexive okay, antisymmetric okay. Now check the transitive. Right, now check the transitive. Now check the transitive. For transitive case, right? For transitive case, we have four cases. Finally, suppose that, right? You can take A, comma B, A dash, B dash, and A dash, B dash, A double dash, B double dash. Case one, if this A less than A dash, this one, A less than A dash, okay, and A dash less than A double dash, okay, then you can have A less than A dash less than A dash less than, sorry, A double dash. You can have A less than A double dash. This one means A comma B related to A double dash B dash B double dash. Case 2, so many cases. Suppose if x1 less than x2, an equal case also, s1 equal s2, then s2 equal s3. Suppose s2 equal s3 means similarly s1 less than equal s3. Okay, s1 less than equal s3. Right, s1, sorry, sorry. If a, a comma a dash. Here a dash, a double dash equal, okay. A dash, a double dash equal. This case a a double dash. A double dash. Okay, a double dash. So in this case also a comma b related to a double dash b double dash. Here's 3. Now you can consider the equal cases, right? If x1 equal x2, and here you can take s2 less than s3. In this case also you put s2 as s1, therefore s1 less than s3. So sorry, with everything you remember, a dash, a dash, a double dash, therefore here again a, here a double dash, therefore here again a comma b, proceed a double dash b double dash. This is the case 3. Case 4, right? Case 4, right? Case 4, As case 4, as case 4, if equal case A equal A dash and A dash equal A double dash, but we have then remaining we have y less than equal y sorry uh, b no b less than equal b dash and b dash less than equal to b double dash, b dash less than equal b double dash. From these things, this implies that a equal a double dash from this two, and b less than equal b dash, but b dash less than equal to b double dash, therefore b less than equal b double dash. From this two, you can write a comma b, write a comma b. So proceed a double dash b double dash. Each of the cases is satisfying, therefore transitive code. Therefore, this one is transitive. Therefore, it is transitive. Therefore, transitive. Therefore, it is transitive. Transitive means therefore reflexive exit, antisymmetric exit, transitive exit. Therefore, it is a partially ordered set. Okay, it's a partially ordered set. Set A cross B, no? Yeah, set A cross B. Okay, A cross B. Set A cross B relation. The relation this one is ordered set, partially ordered set, and each of the elements are comparable. Therefore, it is a totally ordered set, right? Okay. And you have a comma b is proceed a dash b dash means, right? You have, right, this one implies you have either a less than a dash or a equal a dash and b less than equal b dash. Therefore, each of the elements are comparable, right? Therefore, each of the elements comparable. Therefore, each of the elements are comparable. Therefore, each of the elements are comparable. Okay. Here each elements are comparable, right? Each elements of each element of a cross b are comparable. Therefore, uh, this a cross b, uh, a cross b, right? A cross b, and this is the totally ordered set, right? totally ordered set. Okay. Next example, let AI I belong to index set be a totally ordered family of pairwise disjoint totally ordered sets, right? Let AI be a totally ordered family of pairwise disjoint totally ordered sets. Ordered sets. Then the union of AI I belong to index set is a totally ordered set, right? Is a totally ordered set unless otherwise stated. Otherwise stated as follows, right? That means suppose AI are totally order set, then union of AI also totally order set. Because AI are totally order set means each of the AI are reflexive, antisymmetric, transitive. Therefore, you take the union, then that one also reflexive, antisymmetric, transitive, and also each of the suppose you take two elements A comma B belong to AI, but A is totally order set no. Therefore, A B are comparable. Suppose A B are comparable, union of AI elements A comma B also comparable. Therefore, union also comparable. Okay. Uh, this part you prove. You want to prove. Let as follows. Let A comma B. Okay. A comma B. Let A comma B. Let A comma B belong to union of AI. I belong to index set. Hence, there exists J comma K belong to index set such that A belong to, you can take arbitrary A belong to AJ and B belong to AK. A belong to AJ and B belong to AK. This I and K are comparable. Now, sorry, J and K. J proceed K comparable and A proceed B is also comparable. And if both are equal case, J equal K case, then right, then A and B are ordered by the ordering of AJ. Of AJ. Both are equal case consists only AJ, right? Ordering of AJ. Okay. the ordering of aj, right? Suppose you take two elements a comma a belong to union of ai, therefore a comma a belong to particular aj, j belong to index set. You want to prove this example, I will give you, right? I will give you to do this exercise, right? You want to show that union of a is a totally ordered set, right? Union of a is a totally ordered set, right? Union of a is a totally ordered set, right? You can do this part, right? Next one, remark. Generally you can generally uh, you can if you generally you can give the name, right? Generally order means it is a, right? Generally the word order will frequently be used instead to either partial order or total order, right? Both are is possible, right? Order means partial order and total order. Okay, this part you can do it, right? This example, the union of totally ordered set is a totally ordered set. Remark. The word order will frequently be used instead of either partial order or total order, of either partial order or total order, right? Every subset of totally ordered set is a totally ordered set, no? that part that part it's end of that totally ordered set part. Hereafter some little part they are to the totally ordered set, right? Hereafter I will move to the case diagram. Okay, I think it's a video number 4. Then you can easily, I will upload it in the Google Drive. Then you can easily watch it and you can study.